Hello guys, hope you are doing well. In this video I'll be talking about chapter 2. As you know, chapter 2 is all about three sections. The first section is about the acids and bases in general. We will be talking about their properties, some of the industrial acids, and then we will be talking about the nomenclature of the acids, and then about the bases as well. And we'll be talking about the first definition of the acids and bases, which is the Arrhenius acid and base definition. The second section will be about the two other definitions of the acids and base, the Bronsted-Lowry and Lewis acid-base definition. And the third section will be about the conjugate acids and bases and with their strengths. And also we'll be talking about neutralization and the acid rain as well. Let us start from the section 1, guys. At the beginning of our section, provided some of the acids and bases which are commonly used in our daily basis. Let us talk about those acids and bases which we use in our daily basis, guys. The first one, let us talk about the common acids, guys. What's important to be known for these common acids and bases, the product that we use and the acid which is consists in those products. For example, what product that we use, the milk, in our daily life we use milk, and the milk contains what type of acid? Lactic acid. And the vinegar that we use contains acetic acid. The citrus fruits like lemon, orange, and grapefruits that we use contains citric acid. The grape juice that we drink in our daily life contains the tartaric acid. And the malic acid is in apple, guys. The phosphoric acid, which is in carbonated beverage as well. The carbonated beverage, they use the phosphoric acid, or we can say soft drinks, guys. The formation of the vinegar can be formed through the fermenting the juices. Whenever we ferment the juices of some of the fruits, we will be able to obtain the vinegar, guys. So in general, we have to know the acids and the products. For example, may ask, milk contains what type of acid? You have to know that it's lactic acid, citrus fruit, citric acid, carbonated beverage, phosphoric acid, and so on for the other acids. How about the bases? The bases, we have got ammonia, guys. The general household cleaner, ammonia, is a household cleaner. The ammonia use it in the cleaning agents, as a cleaning agent in the cleaning stuffs in our daily life. And then sodium hydroxide, which has a common name of lye, is a strong base and is ingredient in commercial cleaners. The sodium hydroxide and ammonia, they both use it as cleaning agent, but the ammonia is a weak base and use it for to clean some of the stuffs which they do not need a strong cleaning agent. But sodium hydroxide is a strong cleaning agent, can be used for to remove the impurities whenever it's not easy to remove on the surface. We have three other common bases, guys, which we call them as the antacids. They act as to reduce the acidity in the medium. The first one is the magnesium hydroxide, which we call as the milk of magnesia. Magnesium hydroxide, MgOH by 2, belongs to the second group hydroxides. But this is one of the exceptional which we have discussed about in chapter 1. It's not highly soluble, it's not very soluble in water, it's slightly soluble. That's why it's gonna produce low amount of ions, and the concentration of ions of hydroxide is existed in a low percentage, low concentration. That's why it can be classified as weak basis, and this is used as the antacid to relieve the pain in our stomach. Whenever there will be a high acidity in our stomach, we will take the pills of milk of magnesia, and it's gonna reduce the acidity and increase or neutralize the acidic medium and increase the pH of the medium. And the two other, bases which they work as antacid, aluminum hydroxide and sodium bicarbonate, they both work as antacids. So we have got three antacids: magnesium hydroxide, aluminum hydroxide, and then sodium bicarbonate. These are all antacids. We mean they work to remove the or to reduce the acidity of the mediums. Guys, let us talk about the properties of the acids. We have got some of the properties of acids and bases. We'll be talking about them in detail. But each of them, they have five properties. They have got five properties. The properties, only two of them they have. Two of those properties are not in common between the acids and bases, but three of those properties are common in between the acids and bases. We'll be talking about them in detail. So the first property of the acids, guys, is that whenever we want to test the acidic solution or the acids, the solution tastes sour. So they have a sour test. In terms of testing the solution tastes sour. And the second property is that the acids and bases, they change the color of acid-base indicators, guys. We will be talking about indicator in chapter 3 in detail in pH and titration, but a simple introduction for the indicator is that the indicators can be the weak acids and weak bases, which are organic compounds usually. Their property is that they are sensitive. Their color is sensitive for changing pH. As the pH of the medium changes, their color changes with the pH. And the acidic solution, they have a low pH, and the indicator, of course, are sensitive in the acidic solutions, and they change color in the acidic solution. And usually when we dip a strip of pH paper into vinegar, for example, here in this figure, it turns red. This is a litmus paper. A litmus paper somehow is different from the indicators, because the indicators can be used for measuring the pH of solution, but a litmus paper, it only used for determining whether the solution is acidic or basic. It turns two colors, the litmus paper. It can be red for the acidic solutions and the blue for the basic solutions. The third property of the acids is that some of the acid react with the active metals to produce hydrogen gas behind. And the product of the acids, the metals, usually the active metal plus the acid, they have a general equation which they will produce a salt plus H2 gas. A salt plus H2 gas. Here we have got some examples. For example, zinc reacts with H2S, sulfur, which is a strong acid, produces zinc sulfate and releases the hydrogen gas behind. Magnesium reacts with HCl, produces magnesium chloride and releases hydrogen as well. So the acids, they have a property whenever we dip a piece of active metals into their solutions, they're going to react with those active metals and produce the salt with the releasing the hydrogen to the surrounding. Acids, they have other property which they react with the bases to produce salt and water. So whenever the acid reacts with the bases, will produce a salt plus H2O. For example, KOH, which is potassium hydroxide, where the hydrofluoric acid reacts to produce potassium fluoride and formate the H2O to the medium. And usually this type of reaction of the acids and bases we call as the neutralization reaction. We mean one neutralize the other acid is going to produce hydronium, and the bases, they are producing hydroxide. Each they neutralize each other. We'll be talking about that in the third section. Acids conduct electric current. Of course, the solution of the acids, they conduct electric current. The strong acids conduct electric current well, but the weak acids, they conduct electricity purely. And the strong acid like HCl, HBr, Hi, the weak acids like HF, H2S, CS3, COH, they both they are conductor of electricity, but the strongest are weak, strong electrolyte, and the weaks are the weak electrolyte. Among these 5 properties, guys, 3 of them are common with the bases. We'll be talking about also in the bases. The first one, conducting electricity, because both solutions of the acids and bases, they conduct electricity due to of existing ions in their aqueous solution. Second, they both react with each other. The acids react with base, and the bases react with the acids to produce hydrogen, to produce H2O and the salt. The third one, the acids and bases, they are both changing the acid-base indicators. They have got these 3 common properties. Guys, just to recognize the acid solution, we'll be talking about the hydronium hydroxide and pH of the solutions in the third chapter. But the pH of the acid, as you know, that they have a pH less than 7, and the hydronium concentration must be higher than the hydroxide to be acidic solution. And acids, whenever they react with carbonates, they produce salt, water, and carbon dioxide. So keep in mind that whenever an acid, which is HCl, reacts with the sodium carbonate here, the carbonates, they will produce 3 products. A salt, here sodium chloride, and H2O with releasing CO2 to the medium as well. Properties of bases, guys. Let us talk about the properties of bases. As I told you, they have 3 common properties with the acids. The first one, the aqueous solution of bases tests beta. As the aqueous solution of the acids tests sour, the aqueous solution of the bases tests beta. We mean they have a beta test. Unlike the acids, which they have a sour test. The second one, which is the common property between the acids and bases, the bases, they change the color of the acid-base indicator, and in this figure you can see that when we dipped a litmus paper, the pH paper turns blue in the presence of the solution of sodium hydroxide. So it turns blue, the paper. Why? Because it represents the basic solution, and that's why the basic solution, we can say they change the color of the acid-base indicators. The dilute aqueous solution of bases feels slippery like soap, like somehow it's slippery. We can provide an example like soap. There were a ministerial exam question about this, guys. Ask it, which of the following solution feel slippery? So you have to choose the basis as the option. The correct option is the basis, any basis that we have the actual solution, they feel slippery in general. Bases react with acid. This is the second common property between the bases and acids. They react with acid to produce salt and water. Here we have lithium hydroxide with nitric acid, produces lithium nitrate and H2O. This is again is the neutralization reaction, which an acid reacts with the base. The third common property between the acids and bases is that bases conduct electric current. As the acids, they conduct electric current. The bases also, they produce ions in their solution and they conduct electric current. But we have two types of the base solutions. The strong bases, they produce a strong electrolyte solution, and the weak bases, they produce weak electrolyte solution. The strong bases like sodium hydroxide, potassium hydroxide, and so on. The weak bases like ammonia, amine, codeine, caffeine, and so many other bases can be taken as an example. But unlike the acids, the bases, they do not react with metals. So the acids, they react with metal. When we dip a piece of metal into the acidic solution, it's going to react with it. But when we dip a piece of metal into the basic solution, they won't react. That's why we have stated this statement here. Here we have a figure, guys. The figure represents some commonly used acids and bases, guys. This is a ministerial exam question appears in this part of the figure, which stated that fruits and fruit juices contain acids such as citric acid and ascorbic acid. I mean, there should be this should be known for the purpose of the examinations. Guys, we can somehow determine this, summarize this. This is a carbonated beverage. So a carbonated beverage, we said it contains phosphoric acid. But with the phosphoric acid, it has 4 other acids. So the benzoic acid, sorbic acid, phosphoric acid, and carbonic acid, they all are the ingredient in carbonated beverages. So we can say that the carbonated beverage in general, it contains benzoic acid, sorbic acid, and carbonic acid with phosphoric acid as well. But the citrus fruit, this is an example of the citrus fruit. We said citrus fruits, they contain citric acid, but additionally from this figure we can determine that it contains citric acid with the ascorbic acid as well. So the ascorbic acid and the citric acid are the ingredient in the citrus fruits. The common bases that we use in our daily life: ammonia, sodium hydroxide, sodium bicarbonate, aluminum hydroxide, and so many other products that are bases we use in our daily life. We will be talking about the acid nomenclature. As you know that we have defined the acids and bases in the first chapter. But we will be somehow take a quick revision on the nomenclature of the acids in this section. You know, guys, we have got 2 types of acids in general. One we call as the binary acids, which we mean they contain 2 elements, and the other we call as the ternary acid, which we mean they have or can consist of 3 elements. The binary acids, we have got 5 binary acids in our curriculum. 2 of them are weaks, 3 of them are strongs. We'll be talking about them. Let us talk about them, guys. The nomenclature of the binary acid, or the structure of the binary acid, is composed of HX, and the X can be the halogens with the sulfur only. The halogens, chlorine, bromine, fluorine, iodine with the sulfur. These are the 5 binary acids. And in order to name them, we have to add a prefix of hydro. So a prefix of the hydro. The root name, meaning the chlor, brom, iod, sulfur, and fluor. And then the suffix of IC. We have got HCl, HBr, HI as the strong binary acids, and HF, H2S as the weak binary acids. Hydrochloric acid, hydrobromic acid, hydrofluoric acid, hydroiodic acid, and hydrosulfuric acid are the names for the all binary acids. As I mentioned here, there are 5 binary acids. HF and H2S are weak, and HCl, HBr, HI are the strong binary acids. The other type of the acid are ternary acid. The ternary acid, commonly we have oxyacids, but beside the oxyacid we have an example, HCN. It's not oxyacid, is neither oxyacid nor binary acid. We call as the pseudo-binary acids. So the pseudo-binary acid, guys, like HCN. HCN is the pseudo-binary acid. It's not binary. Why? Because it consists of 3 elements. It's not oxyacid because it does not consist of oxygen. In between, it's pseudo-binary, and this type is the only acid which is weak acid, and we named it according to the nomenclature of the binary acids. This is hydrocyanic acid. Hydrocyanic acid. Let us talk about the oxyacids, guys. Oxyacid are those acids which consist of 3 elements: hydrogen, oxygen, and usually one of the nonmetals. We have got 2 types of the oxyacids, guys, but generally we can say that we have some properties of the oxyacids. We have to know that all oxyacids contain hydrogen and oxygen. So all of the oxyacids contain hydrogen and oxygen with additional of the nonmetals. Guys, if we take the difference between hydrogen and oxygen, we mean the number of oxygen minus the number of the hydrogens, or subtracting the hydrogen from the oxygens. If it results 0 and 1, the acid becomes weak. Results 0 and 1, the acid becomes weak. Examples like phosphoric acid, H3PO4, 4 minus 3 results 1, so it's weak acid. 3 minus 2 for carbonic acid is 1, so it's weak. For hydrobromous acid is 1 minus 1 is the 0, so 0 and 1 they have the subtraction of the hydrogen from oxygen results 0 and 1, it becomes a weak acid. Another for the strong oxyacids, guys, if the difference between oxygen and hydrogen, or subtracting the hydrogen number from the oxygen number, results 2 and more, or we can say above 1, 2 and more, it results the acid becomes an acid which we classify as a strong oxyacid. Examples like HClO3, 3 minus 1 is 2, H2, SO4, 4 minus 2 is 2, HNO3, 3 minus 1 is 2, HiO3, 3 minus 1 is 2, and so on, can be stated as examples for the strong oxyacids. For the naming of them, guys, the naming, the nomenclature of them, it depends on the polyatomics, or we can say oxyanions. Oxyanions are those polyatomics, they consist oxygen in their structure, and according to the oxyanions, there are some oxyanions that ends with the ATE. So as the ending of the oxyanions, the polyatomics, is ATE, we replace those ATE for the acidic name as IC. It becomes the IC. For example, guys, NO3 negative is nitrate, but as it becomes HNO3, by addition of hydrogen to the oxyanion, it becomes nitric acid. Just we replace the ATE by IC. S3PO4, it comes from the phosphate plus hydrogen, it becomes phosphoric acid. The same for the chloric acid, bromic acid, and so many other examples can be stated. So in Ministry of Exam, this appeared in one of the rounds in Ministry of Exam said, the polyatomic that ends with ITE, the acidic name take the suffix of what? IC, of course. So you have to know what it will take. But if guys take us the polyatomic has the ending of ITE, not ATE, one less oxygen usually than the ATE, it becomes, we replace it by OUS for the acidic name, For example, here we have an example, HNO3, it combines from, formed from the combination of nitrite, which is HNO2, and nitrite with the hydrogen, it becomes nitrose for the HNO2, which is the acidic name. Other example, H2SO3 sulfite, it becomes sulfurous acid. Chlorous acid, bromous acid, nitrous acid, and so many other examples. So the polyatomic that ends with the suffix of ITE, we replace the ITE to the OUS for the acidic name. Guys, here we have a note. I will be discussing about this note and come back to explain the other parts. Most oxyacids take suffix of ATE in oxygen 3. What do we mean? We mean the oxyacids, they have several forms, usually from 4 forms. Oxygen 1, 2, 3, 4. The oxygen 3 for most of the acids is the ATE form, and that becomes what the IC, as we name the acid, as we convert the polyatomic to the acid. But exceptional, we have 3 common exceptional in our book: sulfate, phosphate, and chromate. Their oxygen number 4 is the ATE form, or IC, we can say. One more oxygen than the oxygen 3 takes the pair, a prefix of pair and a suffix of ATE, or we can say one less oxygen takes a suffix of IT, one less, it takes a suffix of IT. For 2 less oxygen takes a prefix of hypo and the suffix of ITE as well. Let me provide, here we have got an example. We provided an example. We can say it's what? HClO, HClO2, HClO3, HClO4. So this is not sulfur, this is not sulfuric acid, not chromic acid, and is not phosphoric acid as well. So the oxygen 3 is its common form, which is ATE, chlorate. And as the polyatomic is chlorate, when we convert it into the acidic name, it becomes the chloric acid, ATE replaced by IC. One less oxygen than the oxygen 3 becomes chlorose. Why? Because the polyatomic becomes chloride. Two less oxygen, it becomes hypochlorite. So for the acid, it becomes hypochlorous. The ITE replaced by the OUS. For the acid name, we do not change between the acid and the polyatomic. The prefix is not changing, only the suffix changes. The ITE to OUS, the ATE to IC. One more oxygen than the common form is the HClO4, who takes the prefix of per and the suffix of IC, which becomes the perchloric acid. The same for the bromic acid, which is the oxygen 3 is the common, one less bromose, two less hypobromose, one more perbromic acid. Guys, here we have got the tables in our book to somehow memorize the acids, the binary acids, the table 1. The binary acids, and the table 2, the oxyacids and the oxyanions as well. Almost we have provided tips in the first chapter in order to memorize these acids, and we have defined the binary acid. We said the binary acids are those acids composed of two elements, usually hydrogen with the halogens and sulfur. The oxyacid as well, we define it as those acids which composed of oxygen, hydrogen, and one of the nonmetals usually. The oxyacids, we said they belong to a class of acid we call as the ternary acids. And they usually, the structure of the acids, guys, we may guess whenever we write the acids, for example, H2SO4 and H3PO4. We may guess here because the hydrogen is close to the sulfur and the hydrogen is close to the phosphorus, the hydrogen combined to the central atom, but that's not the case. The hydrogen always in the oxyacids combine with the oxygen, and we'll be talking about that. We will call the hydroxyl group is we'll be talking about the hydroxyl group. They are different than the hydroxides. All the oxyacids, they contain hydroxyl group. And what's the hydroxyl group? The hydroxyl group is the group which the oxygen and the hydrogen, they bonded together in the acids. So here we can say, represent the structure of the oxyacids. As you can see, the sulfur is in the center, double bonded with one of the oxygen, and double bond with the other, or two single bonds with two oxygens. So 4 oxygen are surrounding the sulfur, and the hydrogens, they bonded to the oxygens, not to the sulfur. And here in this structure, it's represent the same for the we can say for the S3PO4, the P is in the center, the central atom, and bonded with 4 oxygens, and the oxygens, they bonded to 3 hydrogens. So this bonding of the oxygen and hydrogen we call as the hydroxyl group. We'll be talking about that in detail in the coming sessions. Guys, here we have got some industrial acids. Usually, almost 5 acids in our curriculum talked about the properties of 5 industrial acids. These are the acids that commonly used in industry, and then we'll be talking about the property of each of those acids and the application as well. The first one is H2SO4, which is the sulfuric acid. Sulfuric acid is the most commonly produced industrial acid. So Among the acids, the other industrial acids, this ranks the top in terms of production. It produces in the most commonly produced industrial acid. As it has most production quantity, there should be several applications of it. So there are so many applications. It's used in the production of 5 products like metals, papers, paint, dyes, and detergents. The metals, for the production of the metals, the papers, paint, dyes are the colors, and detergent which we use for cleaning agent. And also, guys, additionally, it's used for is the liquid in the automobile batteries. We call as tezab. The liquid in automobile battery is the H2SO4 and is very corrosive for our skin. We'll be talking about the property of that. So in general, it's used for the production of metal, paper, dyes, detergent, and the automobile battery. It's in the ingredient of the automobile battery. Other property which the sulfuric acid it's famous by that property. It's used as it attracts to water and is an effective dehydrating agent. Dehydrating, we mean the water removing agent. Guys, we talked about dehydration in ionization, if you remember, in the first chapter. Dehydration is when an ion or a molecule surrounded by water and water attracted to it. But the dehydration, we mean removing water from the molecule or the ion. So whenever you remove the water, it becomes dried, dehydrated. And dehydrated is a scientific name for combustion, burning. We call as burning. Whenever sulfuric acid reacts on a surface of the organic compounds, usually it dehydrates them and remove the water. We mean to burn those organic compounds. It can be used to remove water from gases with which it does not react. So whenever we have the gases that contains vapor, it can be used to dehydrate the gases and left the gas behind and remove the water in those gases. The other applications for the sulfuric acid is used in petroleum refining and metallurgical industry and used for the manufacture of fertilizer as well. Guys, for the petroleum industry, it has a great majority applications, the sulfuric acid, and also in industrial metallurgical industry, it has applications. Additionally, it can be used as the plant feed, like the fertilizer, and the other property is that sugar and certain other organic compounds are also dehydrated by sulfuric acid. So this experiment can be done whenever we have an amount of sugar and pour H2SO4 on it. In 2 minutes, 3 minutes, the sugar turns into a black compound, almost like the charcoal, and then it releases a gas which it has an unpleasant odor. This is a simple example, and that's the procedure of burning sugar whenever the H2SO4 removes the H2O in the sugar. As I told you, the skin contains organic compounds that are attacked by H2SO4, and the H2SO4 causes the burners on the skin. So it's very corrosive for our skin. We have to use it with the highly safety guidance in order to not attack our skin because it's corrosive. But 2 key words that the sulfuric acid recognized by are the automobile battery and the dehydrating agent. These are 2 main keywords in Ministry of Exam appears several times. Nitric acid is the second acid which has many industrial application. Guys, it has a property. Nitric acid is a colorless, is a volatile, unstable liquid that stains protein yellow. At the beginning, it's a colorless acid, and in terms of stability, it is highly unstable, and it stains protein yellow, as it represents in this figure, guys. The leather is this leather is protein. So whenever we immerse a piece of leather into the nitric acid, the changes the color of the protein to yellow, stains the protein yellow, and this is one of the keywords that we recognize the nitric acid by. We said it's the volatile and highly unstable. Volatile, we mean it has a high tendency to escape into a gaseous state. How to let it to be stable? Of course, whenever we dissolve this acid in the H2O, it becomes stable. So dissolving the acid in water makes the acid to become more stable than itself as non-dissolved acid. Solutions of nitric acid are widely used in industry. The filter was stained by nitric acid, as I told you. The filter, guys, in this figure, stained by nitric acid, and nitric acid has a suffocating odor, and it stains skin and can cause serious burns for our skin. So it's very corrosive for the skin. In terms of reaction with the skin, it's used as the explosive agent in the explosives. This is the second main keyword for the nitric acid. The first is the stains protein yellow, appears in ministerial exam several times, and then the second one is used as the explosive agent for the explosive bombs. Why? Because it contains nitrogen, and you may have heard the nitrogen bomb. The nitrogen is very explosive, that can be used for explosive bombs. In terms of the other applications, it's used for the production of rubber, plastic, dyes, and pharmaceutical products. For the pills, for the medicine, it produces the medicines. In terms of color, guys, it passes through three colors. First of all, at the beginning, initially it's colorless. So initially it's colorless, but when it decomposes, it becomes Brownian. However, upon standing, they gradually become yellow because of slight decomposition of Brownian nitrogen color. Guys, here we have got the decomposition of the nitric acid. When the nitric acid decomposes, it's going to produce NO2, H2O, and oxygen. Guys, the NO2, its color is brown, a brown gas. So it passes through three colors. At the beginning, it's colorless. During the decomposition, it becomes Brownian, and then eventually it turns to yellow solution. That's in terms of color of the solution of nitric acid. The third acid which has industrial application is phosphoric acid, and the phosphoric acid is commonly known for the acid which is in carbonated beverages. Phosphorus, along the nitrogen and potassium, is an essential element for plants and animals. So, guys, the phosphorus, and as the phosphoric acid contains phosphorus as well, it's one of the ingredients which is mainly used, essential for the animal feed, and as the nutrient for the animals, and as a fertilizer for the plants. So it's used in manufacturing of fertilizer and animal feeds. The first application is what it's used for the nutrients for the animals and the fertilizer for the plants. In terms of taste, the dilute sulfuric acid has a pleasant but sour taste and is not toxic. Because of this property, it's not toxic and it has a pleasant taste. It has been added for the carbonated beverages in carbonated beverages industrial processes. It's used in flavoring as the flavoring agent in beverages and as cleaning agent for dairy equipment. As I told you, the mainly application of the phosphoric acid, the most commonly application of this acid is what is the used in carbonated beverages, the soft drinks, and then additionally it can be used for the animal feed and plant feed, and then for the cleaning agent of dairy equipment. Because it's not toxic, guys, for those dairy equipment like the tankers, the storages, the pipes, and so many other equipments used in the dairy industry. The phosphoric acid used to clean those pipes and storages in order to clean, and then it's not toxic. That's why it can be used for the equipment of dairy industry. Phosphoric acid has got two other properties. It's used for the manufacture of detergent and ceramic as well. These are all the application of phosphoric acid, and the next acid is stomach acid. We call as the stomach acid. Why? Because it releases by the stomach. Hydrochloric acid. The hydrochloric acid is the acid which has many applications. We will be talking about it. The first one, guys, is used for pickling processes. The pickling process, guys, in the industrial acids, the industrial processes, there are in steel industry and iron industry, there are pools. The pool, they have filled the pool with the HCl solution, and then the HCl has a property which it removes the surface impurities. For example, suppose we have a piece of rusted iron or steel. When we immerse this piece of rusted iron into the HCl solution and stays for a period of time, then the impurities on the surface, it removes the impurities. Suppose the red line is the impurities on the surface, it removes the impurities, it becomes a fresh iron without impurities, has no unimpurity. This is the pickling process, guys. When we have a rusted iron, its surface has many impurities. When we immerse this rusted piece of iron and stay for a period in HCl solution, and then it removes the surface impurities of that iron piece. That's the pickling procedure, and is the immersion of metal in an acid solution to remove surface impurities. This is the main one of the main applications of the hydrochloric acid. The other usage is used in cleaning agent in food processes and in the activation of oil wells. And one of the other main applications is used for recovery of magnesium from seawater. It can be used for recovery the magnesium from seawater. It was the Ministry of Exam question, and is the production of other chemicals. It's used for the production of the other chemicals. It's used in to maintain the correct acidity in swimming pools and to clean masonry. It's used for the cleaning agent for the masonries and to regulate the pH of the swimming pools, and it's used we call as the stomach acid, and it's used as digestion agent in the stomach to our stomach, guys. Because the three keywords can be used to recognize the hydrochloric acid, the stomach acid for digestion, recovery of magnesium from seawater, and pickling procedure, which is to remove the surface impurities on the surface of iron and steel. The last acid, industrial acid, is acetic acid. And acetic acid usually commonly recognized for the vinegar. So the acetic acid, pure acetic acid, is a clear, colorless, and pungent smelling liquid known as glacial acetic acid. Guys, in terms of color, it's a colorless, it's clear acid, and in terms of smell, it has unpleasant smell, it's pungent smelling, like a spoiled egg. In terms of the name, it has a secondary name we call as a glacial acetic acid, and it was the ministerial exam question. This name, glacial, means the ice. Why? Because acetic acid has a high freezing point. Its freezing point almost 17 Celsius. So sometime at room temperature, close to room temperature, it freezes, appears in crystal form. So this name is derived from the fact that pure acetic acid has a freezing point of 17 Celsius. It can form crystal in a cold room, especially in winter when the degree temperature is below 17. The acid almost appears in a crystal form. That's why they call it the common name of this acid as glacial acid. The fermentation of certain plants produce vinegars containing acetic acid. So how we can get the fermented fruits? When we ferment fruits, they contain acetic acid. The white vinegar, guys, which we use, it contains 4 to 8% acetic acid. So the white vinegar that we use, it contains 4 to 8% acetic acid. Acetic acid has the other applications. It can be used for the production of plastic and as fungicide as well. It can be used to produce the plastic and as fungicide to kill the fungi. This was all the industrial acids, 5 industrial acids we talked about. What's important, the keyword is that we said, for example, for sulfuric acid, is automobile battery and dehydrating agent. For the other is nitric acid, explosive agent, and stains protein yellow. For phosphoric acid, carbonated beverages. For hydrochloric acid, pickling, stomach acid, and recovery of magnesium from seawater. Acetic acid, the vinegar is the keyword for acetic acid, and fungicide as well. The first definition of acids and bases, which situated in the first section in our book, we will be talking about the first definition, which is the traditional definition of the acids and bases. And that definition is the Arrhenius acids and bases. Let us talk about the Arrhenius acid first. What are the Arrhenius acids? How Arrhenius defined the acids? Classify the groups of acids as what? Guys, Arrhenius acid is a chemical compound that increases the concentration of proton, or we can say hydronium, in the aqueous solution. But guys, this is the Arrhenius has some restrictions, 3 restrictions, or the definition depends on 3 pointers, conditions. The acid must meet these conditions in order to be Arrhenius acid. First of all, increase hydronium concentration. Second, we have some acids, they increase hydronium, but they are not classified as the Arrhenius. After that, this must be a neutral compound or a neutral substance. The ions cannot be classified as Arrhenius. And then the third, it must be in aqueous medium. Aqueous medium. These three conditions are must for an acid to be classified as the Arrhenius acid. Guys, Arrhenius acid are molecular compound with ionizable hydrogen atoms. So all of the Arrhenius acid, they must have hydrogens, which are we call as the protons, and must donate those protons in order to attract with water and produce or increase hydronium in the aqueous solution. Arrhenius acid solution are known as the aqueous acids. Why? Because the Arrhenius just defined the acids in aqueous medium, not in other mediums. All aqueous acids are electrolytes. Of course, you know that whenever it's strong or weak, they are all electrolytes. An acid will ionize in water and will increase the number of hydrogen ion, we mean the proton, present in the acid molecule. And the acid molecules are sufficiently polar so that one or more hydrogen ions are attracted by water molecule and negative charged particles left behind. The hydrogen ion in aqueous solution best represents the hydronium, so the H, the proton as itself, as this individually, has no existence in the solution. Instead, as the acids, they donate or release the protons into the aqueous solution, it has immediately bonds with the H2O to form hydronium. According to the Arrhenius, water is just a solvent according to the Arrhenius definition, and is neither a base nor acid. In terms of the classifying H2O as what, he said it just acts as a solvent, neither acid nor base. That's the Arrhenius definition for H2O. And in terms of reaction, the Arrhenius has no reaction. So whenever asked in ministerial exam about this reaction represents the which definitions, it belongs to the which acid-base definitions, Arrhenius must be discluded from the options. An example here we have HNO3 nitric acid, guys, with the H2O. And nitric acid, it's gonna donate one of the hydrogens to the H2O, release the hydrogen, and then increase the hydronium concentration in the solution, and then left the nitrate behind as well. So we can say nitric acid is Arrhenius acid. Why? Because it's in aqueous medium and it's neutral and it increases the hydronium concentration in the solution. But let me provide another example. HS negative plus H2O will produce hydronium plus S2 negatives. Guys, here HS increases the hydronium concentration, so meets the first condition. How about the second? Is that neutral? No, it's ion, so it's not Arrhenius acid. Despite of increasing hydronium, Arrhenius was not able to define the ions. He just defined the neutral compounds. Another example, for example, when we have the gaseous HCl in the gaseous state and the ammonia in gaseous, this can be obtained from the hydrochloric acid. The hydrochloric acid, there will be escaping of the hydrogen chloride gas from the solution, and this from the ammonia solution, which is ammonium. escaping of these two gases to the surrounding, the medium changes to the gaseous medium. And then when they react in the gaseous medium, they will produce NH4Cl. Okay, guys? This can be stated as what? The reaction. These two are not the Arrhenius acids or Arrhenius bases. Why? Because the medium of the reaction is not in aqueous medium. The medium of the reaction is not in aqueous medium. This, separately will increase the hydronium, and that one will increase the hydroxide. But none of these two are classified as the Arrhenius acid or Arrhenius base. Because of that, it's not in aqueous medium. Here we have got some common aqueous acids, guys. Those acids which we talked about, strong acids and weak acids. We talked about the strength of in terms of the classifying the acids, the acid nomenclatures. Let us talk about the acid strength. The acid strength depends on several factors. We will be talking about their strength in detail. Guys, the first factor which the acid depends on the strength of the acid is the polarity. Polarity, we mean the polarity of the bond between the hydrogen and the oxygen. Guys, polarity refers to the attraction of two atoms to each other. If the attraction or the electronegativity difference between those two atoms is in between 0 to 0.3, we will get a nonpolar bond. But if it's in between 0.3 to 1.7, it becomes a polar molecular bond. If it's above 1.7, it becomes an ionic, which is highly polar bonds. But how to know how the polarity affects the strength of the acid? Guys, as the polarity of a bond increases, the bond becomes weaker. It becomes weaker. The weakness of the bond increases. So, as the bond becomes weaker, how it will be the breaking process? Can be breaking easily. So the breaking procedure becomes easy. Easily we can break down the bond. And as the hydrogen with the oxygen, the bond between hydrogen and oxygen broken down, or the bond between hydrogen and the nonmetals in the binary broken down easily, so the concentration of the hydronium increase. That increases the concentration of hydronium. And guys, for the acids, any factor is increase the hydronium concentration. Any factor increase the concentration of the hydronium in the solution, that can be classified as the factor behind the strength of the acid. So the strength of acid increase. So guys, polarity increase lets the bond becomes weaker. As the bond becomes weaker, it can be broken easier, and then increase the hydronium, and then acid strength increase. So the polarity is directly proportional with the strength of the acids. Second, guys. Second, we have bond energy. Bond energy. Guys, the bond energy is amount of energy which required to break a bond. In order to break any bond, we have to provide somehow energy. And the amount of energy which we provide to break the bonds we call as the bond energy. Logically, if a bond requires more energy to break down, that means the bond is difficult. I mean, the bond is strong. Almost the bond is strong. And as the bond is strong, the donation of the proton becomes lower, less, and then that will reduce the strength of the acid. So guys, as the bond energy increase, bond strength increase to bond strength of the bond, but strength of the bond is inversely with the polarity. As polarity increase, strength of the bond decrease. It becomes weaker, as we said. That can be stated as strength of the bond. So as the bond energy increase, the bond strength increase. As the bond strength increase, the bond becomes stronger. Breaking becomes difficult. And as the breaking process becomes difficult, there will be fewer hydronium in the solution, and then the strength of acid decrease. So the bond energy increase the strength of the bond and lets the bond to be difficult to break down, become stronger, and then that will reduce the concentration of hydronium in the solution. As the concentration of hydronium reduces, that reduces the strength of the acid. So the bond energy is inversely proportional with the strength of the acid. The third factor, guys, is bond length. Bond length. For the binary acids, guys, unlike the oxyacid, this polarity it was for the binary acids. But for the polarity it was for the oxyacids. The binary acids, for example, HF, the bond between HF is more polar than the bond between HCl, HBr, and HI. But why the HF classified as weak? Because of having a high electronegativity by F, which attracted the H toward itself and produced a short bond between itself with the hydrogen, and the bond becomes stronger to be broken down. So guys, the bond structure can be represented as that: HF, HCl, HBr, and HI. Here we have got the representation. I have represented in this way in order to be somehow easy to manage it. Guys, the bond of as the length of the bond reduces or becomes shorter, the bond becomes stronger to be breaking down. Logically, in our daily life, something that is longer than the other can be broken much easier. So the bond between H and I can be breaking much faster than HBr and then HCl and then HF. So as the bond length reduce, that lets the bond to become stronger. And as the bond becomes stronger, it requires more bond energy to break down. As it requires more bond energy to break down, it becomes weaker acid. So guys, the bond length, let us say as the bond length increase, that we can say increase or reduce the strength of bond. What will happen to the strength of bond? Reduce. Why? Because the bond becomes weaker to break down. And as the strength of the bond reduces, the bond energy reduces as well. And as bond energy reduces, the concentration of hydronium in the solution increases more, and then strength of the acid increases. So from HF toward HI, the bond length increase, and the strength of the bond, it becomes weaker, its strength reduces. And as the strength reduces, that requires lower bond energy, and bond energy reduces as well. And then this lets the solution of HI to produce more hydronium than HBr, more than HCl, more than HF as well. So the strength of the bond increase with bond length. In this direction, guys, we can say, let us change the direction. In this direction, the length of the bond increase and strength of the acid increase, but the bond energy reduce and the strength of the bond reduce as well. So the one that's shortest, it's most difficult to break down and increase the hydronium concentration in the solution. So this can be said HI among the H binary acids is the strongest acid, then followed by HBr and HCl, and then HF, and then H2S, the last binary. This was the bond length. What else remain is the we can say with the bond length we can discuss about the electronegativity. HF, HBr or HCl, HBr, HI. Guys, in this direction, the electronegativity of the halogens increase. So the electronegativity increase. As the electronegativity increase, the bond becomes shorter. Shorten the bond. And then as the bond becomes shorter, the strength of the acid reduces. We can state like that. The electronegativity increase, the acid becomes weaker. Why? Because the attraction to the hydrogen becomes stronger, and the acid attraction becomes stronger, the bond becomes strong to be broken down, and then becomes a weaker acid. This is the fourth factor. The fifth one we will be talking about in detail later. It's about the electron density. Electron density. Guys, electron density, and we can say additionally oxygen number. Oxygen number. How the oxygen number affects us on the acid strength and the electron density? They are opposite to each other. Guys, as oxygen number in an acid molecule increase, that increase the polarity of the molecule, the polarity of the bond between hydrogen and oxygen. And as polarity increase, that reduce or release more hydronium to the solution, and then the strength of the acid increase. So oxygen number increase polarity, increase the hydronium, increase the strength of the acid as well. But how about the electron density? Electron density. As the electron density increase, the oxygen number reduces, polarity reduces, that reduce the hydronium, and strength of the acid reduce as well. What do you mean by the electron density, guys? I will be showing you the structure. For example, Cl bonded with the oxygen and the hydrogen. Cl bonded with the oxygen, one other oxygen and hydrogen. Cl bonded with 3 oxygens and hydrogen. Guys, we are talking about this bond, the electron density in this bond. As you know, the oxygens, they have electrons, free electrons, unshared electrons, These unshared electrons can somehow repel the density of the electrons in the bond. This is, here we have got two atoms of oxygen around the chlorine. As the free electrons, the unshared electrons to the oxygen atom surrounds the central atom, attracted to this bond, and there will be a repulsion force between the electrons in this bond and the electrons there. So it repulses the electrons in the bond. That reduces the bond, the electron density in the bond. That as reduces the electron density in the bond becomes weaker, and the breaking procedure for the hydrogen becomes easy, and the hydronium becomes small in the solution, and the acid becomes stronger. So what we mean by electron density? Simply we mean the density of electrons in this bond. When the oxygen attracted, as more oxygen attracted, that becomes more weaker, and the electron density becomes less, and then that's the relation between the electron density and oxygen number, which is inversely proportional to each other. Guys, the aqueous solution of strong acids, we have got two types of acids, strong acids and weak acids. The aqueous solution of strong acid always contain the hydronium and the anions. The hydronium and anion, they exist in aqueous solution of the strong acid. For example, in this solution here we have got only hydronium and chloride ion. The acid itself has no existence. Why? Because the strong acid, they completely ionize to form the hydronium and an ion. So guys, is one that ionized completely in aqueous solution. A strong acid is classified as a strong electrolyte. The ionization of the strong acid produces hydronium and an ion, but not the acid molecule. So it has no existence in the solution. For all strong acids, the forward direction is favored. In terms of direction, guys, for the strong acids, and strong bases can be stated as well. Always the favorite direction is forward. Always the favorite direction is forward. Strong acid, they ionize 100% in the solution. The strength of the acid depends on the polarity. We talked about the polarity and the bond energy. And additionally, we talked about the oxygen number, electron density, electronegativity, and the bond length as well. A weak acid releases few hydrogen ions in aqueous solution. Unlike the strong acid, they partially ionize in the solution, the weak acids. That's why they release lower amount of the ions in the solution. The solution of the weak acid, guys, contains hydronium, the acid itself, and the anion. But which one in higher concentration? Of course, the acid itself, the concentration of the acid, the weak acid we mean, higher than the hydronium, and the hydronium equals to the anion. Why? Because they are almost produced the same. So most of the acid remain as non-ionized molecules, and the favorite direction for the weak acids is what is the reverse direction. So the reverse direction always for the weak acids and weak bases can be stated is the reverse direction. That's why we have represented by double arrow. In this solution, HCN has the highest concentration, followed by hydronium, and CN, they have equal concentrations. The electron density inversely with the strength of the acid, but oxygen number is directly. We talked about that, guys, as the one of the factors behind the acid strength. Here we have got acetic acid ionized slightly in water to produce hydronium ion and ions. So in the solution of acetic acid itself has the highest concentration, followed by the hydronium and acetate. They have equal concentration. For the acetic acid, guys, it has got four hydrogens. Here we have a property for acetic acid. It has got 4 hydrogens, but only one of them, the bond is polar, and it has tendency to donate only one of them. That's why it has got only one acidic hydrogen, or we can say one acidic proton to be released in the solution. The other 3 hydrogens, they bonded with carbon, and the hydrogen with the carbon, they have a nonpolar bond. It won't dissolve in water, that part, but the polar part, which is H with O, dissolves, and then later the bond breaking down to produce hydronium. Weak acids are weak electrolyte, guys. Ionization of weak acid occur in reverse reaction and represents by double arrow. I told you that the favorite direction for the weak acids are reverse direction. There are 2 factors that the acid strength is independent on. The first one is the hydrogen number, guys. Notice that the number of hydrogen atoms in the formula does not indicate acid strength. For example, guys, H3PO4 and HNO3. Here we have got 3 hydrogens. Here 1 hydrogen, but we call this as weak acid, this one as strong acid. So this, while the H3PO4 has 3 hydrogens and the HNO3 has 1 hydrogen, the number of hydrogen does not indicate the strength of the acid, unlike the number of oxygen. The number of oxygen increase the acid strength, but the number of the hydrogen does not increase the strength of the acid. Second factor which the acid strength is independent on is what is the solubility. It's not the case to say that as an acid is highly soluble, so it becomes a strong acid. No. For example, we have examples. The acetic acid is highly soluble, but is not a strong acid. The acid strength is independent on solubility. It depends on the factors which we talked about, and those factors, they increase the hydronium concentration. So any factor that increases the hydronium concentration can be classified as a factor behind the strength of the acids. Aqueous solution of bases and Arrhenius bases. We talked about the Arrhenius acid and the aqueous solution of the acids, strong acids, weak acids, and the factor that influence the strength of the acids. Let us talk about the aqueous solution of the bases, guys. Bases, according to the Arrhenius definition, are those substances which they increase hydroxide concentration in the solution. So there are substances that increase the concentration of hydroxide in the solution. The 3 restrictions for the acids applied on the bases as well. The first one must increase the hydroxide concentration. The second one must be neutral. The third one must be in aqueous medium. Guys, unlike the acids, which are all molecular compounds, the bases classified into 2 groups of compounds. Some of the bases, a group of bases are the strong, most of the strongest are, all of the strongest, we can say, are ionic compounds, ionic bases. Some of the others are molecular bases, which are the weak bases. So most bases are ionic compound containing metal cations and hydroxide anions. Strong bases dissociate in water because they are ionic. So the strong bases, we talked about them in chapter 1, are the group 1 and group 2 metals plus hydroxide. And all of them, they are ionic compounds, except the milk of magnesia, which is magnesium hydroxide and beryllium hydroxide, because they are not very soluble compounds. When a base completely dissociates in water to yield aqueous hydroxide, the solution is referred to what? As strongly basic. That name refers to we call the first group elements as alkali metals and the second group as alkaline earth metals. Why the alkali and alkaline earth metal? Because they produce high concentration of hydroxide in the solutions. For example, here the first group elements, they called alkali metals because hydroxide of them form alkaline basic solution. Lithium, sodium, potassium, rubidium, cesium, francium. They will produce the cation and hydroxide. So in aqueous solution of the strong bases, only cation and hydroxide exist. Itself has no existence. And the favorite direction for the strong bases are the forward direction. The strong bases, they have a forward favorite direction. Not all bases are ionic. Some of the bases are molecular gases, like ammonia. Ammonia is molecular base, and ionizing water, it's molecular. Why? It ionizes instead of dissociating. For example, here is written ammonia reacts with H2O, produce ammonium and hydroxide. So the arrow represents by double arrow. Why? Because the reverse direction is more favorite. So guys, the strong acids and strong bases, the favorite direction is forward. For the weak acid and weak bases, the favorite direction is reverse, is favorite. Here we have got a group of compounds which we call as the D block metals plus hydroxide, guys. The D block metals plus hydroxide are ionic compounds, ionic bases, but they are weak bases. Like copper hydroxide here is provided in this in this figure. It was the ministerial exam question. It said which of the following is not very water soluble and acts as a weak base. So the copper hydroxide was the option which the correct option was in ministerial exam questions. So this is a gelatinous blue precipitate of copper hydroxide, almost precipitated. Why? Because it has low solubility tendency to soluble. That's why it can be what the hydroxides of metal are nearly insoluble in water. This hydroxide, copper hydroxide, and so many other D block elements can be stated. They are classified as weak bases in terms of groups of compounds. Guys, we talked about we discussed about the strength of the acids. Let us talk about what the strength of the bases depends on. Strength of the bases depend on a factor that what increases the concentration of hydroxide in the solution, that will determine the strength of the bases. So the strength of the base depends on the extent to which the bases dissociate or adds hydroxide ions to the solution. In which extent those compounds, they dissociate or ionize to produce hydroxide in the solution. If they have a high tendency to produce hydroxide, completely dissociate, or we cannot say completely ionize because molecular bases, they are all weak. If they partially dissociate or ionize, they become weak. If completely dissociate, they become strong. For example, potassium hydroxide here, completely dissociate into potassium and hydroxide. So itself has no existence. It can be classified as strong base. Why? Because it completely converts into the hydroxide. And strong bases are strong electrolyte, guys, in terms of their property. Bases that are not very soluble, do not produce large number of hydroxide ions when added to water. Some metal hydroxide, we discussed about that, copper hydroxide, are not very soluble in water. Ammonia, which is highly soluble but is a weak electrolyte, the concentration of hydroxide in the ammonia solution relatively is what? Low. So ammonia, despite of that, is highly soluble. It produces low amount of hydroxide, so it can be classified as weak base. So the strength of bases, guys, independent on solubility and independent on the number of hydroxide in the structure of the base. Independent on the solubility. Why? Because ammonia is highly soluble but classified as weak base because it produces low concentration of hydroxide in the solution. And independent on the structure of the hydroxide in the structure. For example, copper hydroxide has got two hydroxides in the structure, but lithium hydroxide has got one hydroxide. This is a strong base, that's a weak base. So the number of the hydroxide in the structure of the bases does not affect the strength of the base. Many organic compounds that contain nitrogen atom are also weak bases. With the ammonia, the other organic compounds usually they contain nitrogen atom are weak bases, like for example codeine C18H21NO3, which works as a pain reliever and works as the weak base. And here we have the table of some of the weak bases and strong bases, guys, strong acids and weak acids as well. Here we have aniline, ammonia, the copper hydroxide, codeine, amines can be stated as well. Guys, strong bases, this is the point that to differentiate between the strong base and strong acids. Strong base and weak bases. Strong bases are group 1 and group 2 metals plus hydroxide except magnesium and beryllium hydroxide. Weak bases are D-block plus hydroxide, ammonia and compounds containing carbon, hydrogen and nitrogen. So simply these two statements can be used to differentiate between the strong bases and weak bases as well. The same for the strong acids and weak acids. We have discussed about the acids, but in general, what are the differences between the strong acid and weak acid solutions? The strong acid, in terms of conducting electricity, they are strong electrolyte, but the weak acids are weak electrolyte. They have a high polarity of bond, strong acids, but here low polarity, low bond energy, here high bond energy. Completely ionized, partially ionized, has only ions in solution, fewer ions in solution, and more non-ionized molecules. So the non-ionized molecule here is more than the ions. That's the end of the section, guys. Here we have some ministerial exam questions. Let us practice some of them. This name is derived from the fact that pure acetic acid has a freezing point of 17, so the glacial acetic acid, B is the correct answer. The acid is used for explosion. I told you that several times appear in ministerial. Nitric acid. How many acidic hydrogen does acetic acid has? Only one. H3PO4 contains 3 hydrogens and considered as weak acid, but HCl contains 1 hydrogen considered as a strong acid. So which one below does not true for given information above? Is not true. So the keyword here is what? Is not true. Because acetic acid or acetic acid does not depend on number of acidic strength does not depend on the number of hydrogen. The number of the hydrogen does not affect on the strength of the acids. That's true. It said that's not true. It's not true. Because HCl is a polar molecule easily ionized, this is true. Because S3PO for partially ionized, also true. S3PO for ionization indicated by a single arrow, this is wrong. It indicates by double arrow because the weak acids, they are partially ionized. Which of the following is hydration of proton? Of course, the hydronium ion is the hydration of proton. What's the formula of chloric acid? Chloric acid, the D is the correct answer. HClO3 is the chloric acid. So guys, more questions. Which of the following is correct formula for sulfuric acid? None of them, because H2SO4 is the formula. Which solution contains the largest concentration of ion? The largest concentration of iron depends on the number of the factors. For example, HCl has got 2 ion factors, but CaCl2 has got 3 ion factors. Their concentrations are equal, so CaCl2 has the more ion concentration than the HCl. Which of the following is chlorous acid? So chlorous acid is HClO2. Which of the following is the strong acid? Of course, HCl is the strong acid. Which of the following will present in aqueous solution of H3PO4? H3PO4 itself, H2PO4 negative, PO4 negative 3, all of them? Of course, all of them exist in the solution, guys. For this acid is chloric acid, which is HClO3, hypochlorous acid, HClO, and perchloric acid, HClO4. Arrange increase in order of acidity. Increase in order means the least to the highest. So it will be HClO, and then HClO3, and then HClO4 according to the oxygens. So which one is the correct one? HClO, HClO3, HClO4. D is the correct answer. Which of the following is not an oxyacid? Of course, A is not an oxyacid because it's hydrogen peroxide. Dilute solution of weak acid contains which of the following? Hydronium, anion, acid molecule, all mentioned. Which of the following turns color by passing time? The color for the nitric acid, so turns color by passing time. Which type of acid used in cleaning agent, swimming pool, and digestion? Of course, HCl is used for the digestion. When an acid reacts with an active metal, it produces hydrogen gas is produced, so that's correct. Which of the following is the property of a strong acid? Is a strong electrolyte, completely ionized in water, aqueous solution, is good conductor, all of them, all are true. An acid ending with the IC produce an anion with the ATE, of course, suffix of ATE. Which of the following acid is used for identification of protein? Nitric acid. Which of the following property does not belong to acids? Property, change the color of indicator, it belongs. Ionization in aqueous solution, it ionizes. Hydroxide ion produce because they do not produce hydrogen.